All right, let's go ahead and get started. So I'm Robert Heath. This is lecture number 24, Wireless Communications Lab. And today we are going to talk about transmit diversity. And so if you were to explain why exploiting transmit diversity is hard, and what I mean here is that we won't be able to do something, essentially as easy as what we do at the receiver. And then you should be able to derive the maximum ratio transmit diversity solution. And then we're going to look at a special type of transmit diversity, which is an example of what's called a space-time code. And in particular, we're going to look at this Alamo T code. And so we're going to go through the derivation of the Alamo T code. So you should be able to derive it and then show that it has a second-order diversity gain. That's the main things here. A couple announcements before we get started here. I guess one announcement. You should have by now picked up your graded exam and the solutions in the lab session that you had last week. If you have any exam regrade requests, please turn them in to me by Friday. You can put it in the box outside my office, but send me an email that you've turned it in. So that would be by 5 p.m. And there's a regrade request form on Blackboard that you can fill out and attach to your document. And of course, if the points are added up wrong, that's an easy fix. Otherwise, I'll take a look at the problems again. Okay, so to begin here, let's look at received diversity. Just a quick review. So the setup with received diversity, so first of all, remember that the general purpose of diversity was to combat this idea of fading here, so that we have multiple different copies of the signal available at the receiver. And the hope is that each copy goes through a different fading channel. And so if we space the antennas far enough apart, we can say that these channels are roughly uncorrelated. And so if one is fading, the other one may or may not be fading. And so that's a good thing for us. And with received diversity, so the diversity concept itself is about obtaining these different, communicating essentially through different realizations of a channel. And with received diversity, we generate those realizations through multiple receive antennas. Now, one thing I wanted to point out is that there's another subtle benefit of received diversity, which is that you also have the opportunity to experience different noise realizations as well. And so that's captured like down here. And so with received diversity, not only do you have a different channel, you also have different noise. And it's going to turn out that that's going to improve performance a bit further over the transmit diversity case, as we'll see just in a moment here. So I understand Takao went through the derivation of the maximum ratio combining solution and its probability of error analysis. So I'm assuming that you've all seen that. I hope you enjoyed the guest lecture. Anyone here for the guest lecture? Yeah, good. Yeah, I didn't announce it in advance. I was afraid that maybe some people wouldn't come if there was a guest lecture. So, but I hope that you all did enjoy it. He's an actual working engineer, so hopefully he gave you some insight into some of the things that he does. All right, transmit diversity, space-time code. Oh, actually, we're also going to have an introduction to MIMO communication today, too. I forgot that. All right. Okay, so let's get started here with transmit diversity concept here. So we're going to start off with a naive approach that we're going to use to show why transmit diversity is hard. Where is the screen? Okay. All right, so transmit diversity. So the setup here is, like it says here, so we're going to assume multiple antennas at the transmitter. So I'm going to draw my block diagram here with multiple antennas at the transmitter. There's a single antenna at the receiver, and between every transmit and receive antenna, we have a complex channel, H of K here. Now, I'm not going to label yet what we're doing over here at the transmit antennas, because I want to start off with what everybody wants to do at the beginning and show why that's not a good idea. And that's what I'm going to call the naive approach. And this is not its formal name, but it doesn't really have a formal name because it's a bad idea, so we don't give it a name. You could also, I guess, call it stupid diversity approach. And this approach, which seems perfectly reasonable, is just to send the same signal from all the transmit antennas. So that's actually the idea here. Now what we're going to do, though, is we're going to, just to keep things fair, we're going to impose a sum power constraint here. So we're actually going to send, in terms of the discrete time symbol set here, something like this, square root of EX over NT times S. And the square root of EX is such that when you sum the power across all the antennas, the sum is equal to square root of EX here. And so our receive signal, again, assuming, perfect sampling and synchronization, is going to look like this here. So we're going to get Y, I'm going to put Y of N here. There's no index on the Y because we have just one receive antenna. And so we're going to get H1 times square root of EX over NT times S plus H2 square root of EX over NT times S plus ... H of NT square root of EX over NT S plus noise here. Just adding the N index there here. And now, rewriting this, what we're going to see is that, look, we have a square root of EX over NT and an S of N in each of these terms, so we can factor them out. So we can write square root of EX over NT, S of N, and then here I'm going to have H1 plus H2 plus ... H of NT plus noise. Now, we can, for convenience here, we can also let this be equal to here. We can bring the factor of NT over there. Doesn't really matter, but I'm going to rewrite this as square root of EX over nothing here. 1 over square root of NT times H1 plus ... H of NT here plus noise. Now, the question now is really, what is the distribution of this quantity right here? Because this is like the effective channel that we're seeing. So does anyone see, if we assume that the H of K are complex Gaussian with zero mean and unit variance, what is the distribution of this quantity here? Anybody see what that distribution is? Their IID. The same distribution here. So we have to use this fact that I have gathered from Yingzhe that many of you have had trouble with, but it's a fact of property of Gaussian random variables that if you have a sum of Gaussian random variables, the result is also Gaussian. And in particular here, the sum is Gaussian with mean of the sum of the means and the variance, the sum of the variances here. So let's look at this right here. So 1 over square root of EX over NT, H1 plus H of NT is Gaussian. So let's compute the mean. Expected value of 1 over square root of NT, H1 plus ... H of NT is equal to 0, because each of them is 0 mean. So, the sum of 0 is 0. And then, now let's look at the variance here. So it's the variance of 1 over square root of NT times H1 plus ... H of NT here. Now, because they're independent, it's the sum of the variances here. And then the variance of this here, so the variance of the sum, now we have to be careful because we have to take the expected value of the absolute value squared minus the mean. So we're going to have a square here. So this is going to be 1 over nt times the variance of h1 plus 1 over nt variance of h2, etc. here, which is just 1. So then that's nt, 1 over nt's, which is just 1. So what we can conclude here is that this quantity here, 1 over square root of nt, h1 plus h of nt, has the same distribution as complex Gaussian random variable with zero mean and unit variance here. So we can then rewrite the input-output relationship as, we can say y of n, and you see this a lot of times in the literature, this, equality and like distribution here, but, is equal to square root of ex g s of n plus v of n here, where g is my new channel coefficient, and that's 0, 1 here. Now, we have already studied this case extensively. This was the first scenario that we studied, so we know that its average probability of error, has this form at highest NR, where it's something like n minus 1, 1 over ex over n naught. There's 4 d min squared plus 1, something like this here. So we know that there's no advantage to having these multiple antennas. So that's the point here. So there's no diversity advantage. So the approach of sending the same signal from all the antennas, just repeating your symbol, it leads to no benefit at all. And the intuition of that is as follows here. In the maximum ratio combining case, remember that we co-phased before adding the signals. Here, there's no co-phasing. So we have, the signals each see a different realization of this channel, which is pointing in, has an independent magnitude and phase. And so when you add them up, they don't add coherently. And so they just go, all over the place. So this simple approach is not a good idea. But I wanted to show it to you because by doing some basic calculations, you can then derive yourself its probability of error and show why it's not a good idea, as opposed to me just telling you it's not a good idea. Now, let's look at another scenario here. Now, one thing I do want to point out is that there are other potential channel models, and there could be a case where sending exactly the same thing like that on all the antennas works, but it doesn't work in general. So now we're going to look at a generalization of what we did in the last lecture, which is called maximum ratio transmission. Which we abbreviate as MRT. With maximum ratio transmission, what we want to do is we want to solve the problem of those signals not adding up coherently. So what we're going to do is we're going to consider an abstracted block diagram that looks something like this here. And this is not, of course, as detailed as the block diagrams that we do in the in the early lectures in class, but I would expect that you could draw such a block diagram if needed. So we're going to have the square root of ex here, and then we're going to multiply that signal by some sort of a complex number, W1, and I'm actually putting the conjugate here for reasons that will become clear, down through W of nt here. And so this right here this operation here is known as beamforming. And it can actually be performed literally in analog, where you have a device that's called like a phase shifter, and you can have an attenuator that are probably digitally controlled. Most of the time in multiple antenna systems, the beamforming is done in digital, and so this operation would actually be done before the digital to analog converter. And so you could build that in, you could put it, you know, in our match filtering operation at the transmitter, or pulse shaping, or somewhere before that. But mathematically, this block diagram here is sufficient. So we're going to send the same signal on each antenna, but we're going to scale it by this W here. Now, I didn't put the division by NT here just because of how I'm going to normalize the W's, but I'm going to normalize the W's so that the transmit power is totally fair. So this is our transmit structure here. We have the same assumptions about the channel, same receive antenna setup here with noise, and you know, channel estimation and detection and so on here. So what I find it convenient to do here is, just like we did with maximum ratio combining, is to write everything here in vector form. So we're going to define a vector H that has all the coefficients of the vector of the channel here. And then, yeah, I'm just thinking here because I often write it in a slightly different way here. All right, that's fine. I'll use this approach here. This H here, let's write this W like this here, W1 through W of NT. And then what we see at the receiver here is a sum of W1 conjugate times H times S plus noise plus W2 times square root of EX, H, S plus noise, etc. here. So we can rewrite that in a form that looks almost exactly like what we had before with maximum ratio combining. So we're going to have square root of EX here. We have a W star H times S plus noise. And this noise here is not scalar. So we have that the effective transmit beamforming is effectively an inner product between this beamforming vector W and this channel vector H here. Now, so I'm writing this in a way that looks like what we did before here, but you can often, if you take my MIMO class, I'm actually going to write this as something like H star W for when we look at generalizations with multiple transmit and receive antennas, it makes sense. So we can apply kind of the same principle that we did for maximum ratio combining, which is that we have some intuition that, you know, the optimum W here should be parallel to H. But to formalize that, let's look at the problem here. And so then also, yeah, I want to ensure that, so this is the input-output relationship, and then we need to have W star W equal to 1 to satisfy the power constraint. Okay, so now let's maximize this SNR to find the optimum W here. So to find the optimum W here, so we're going to maximize W star H norm squared EX over N naught, subject to the norm of W squared being equal to 1 here. Now, we already know from what we did last time that you know, this W star H norm squared EX over N naught is less than or equal to some alpha squared H star H squared EX over N naught where the optimum W then is equal to some scalar of the optimum of the channel there, H. So it's kind of like a match filter here. And now to enforce the power constraint, we plug this in here, and we see that W star W is equal to, alpha could be complex, we get alpha squared H star H. So therefore we can take that magnitude of alpha squared, this should be equal to 1. So that alpha squared should be 1 over essentially the magnitude of this vector here squared. And so you have a degree of freedom here because the phase is unspecified, so you can put whatever phase you want, but we typically take just alpha to be 1 over the norm of H squared here. Okay, and so with that, we get that the optimum beamformer is equal to H divided by the norm of H here. And then, sorry, this is the square root here, so, yeah, sorry, I forgot the square root here. So it's just equal to the channel divided by suitable normalization. And so that's it here. Now, if we look at the intuition here, so what's going to happen here is that we get sums of the form WK star times HK. And if you look at what WK is, well, WK is HK. So we get, this is equal to HK star over HK divided by the norm of H here. And this is where the coherence combining effect kicks in. It's right here. Right, so if you multiply complex number by its conjugate, the output's always real and positive unless, of course, there's 0. Okay, so that's the performance there. Let's see, what else am I missing here? Oh yeah, probability of error analysis. So let's look at what's the diversity advantage that we achieve here. Well, with the optimum solution, this instantaneous SNR is equal to W star H squared EX over N naught, which is equal to H star H EX over norm of H squared EX here, sorry, N naught. And then, so we just have the norm of H squared divided by the norm of H squared. So that's just equal to the norm of H squared EX over N naught here. I'm just thinking here, I still think I need a normalization here. Where did it go? Okay, so hopefully this is correct here. So the probability of error will then be something like 1 over square root EX over N naught, for N naught, d min squared plus 1 to the NT here. Yeah, this is correct here. So what we see is that effectively we get exactly this full diversity advantage here as was characterizing the exponent of the SNR, and there's otherwise really no loss here because so we'll get a loss with the next strategy I show you here. But this is one of the intriguing things that, so if you have the ability to do this beamforming here at the transmitter, you can get the same effect as having it at the receiver, which is nice, at least in terms of reliability here. Now, why this is important is that if you think about systems like cellular systems where you can put a lot of antennas at a base station, but maybe not at the handset, this transmit diversity allows you to leverage those antennas. Whereas, you know, if you have receive diversity but you don't have multiple receive antennas, you're out of luck here. So that's the idea of transmit diversity here. And this is maximum ratio transmission, basically a match filter, just the counterpart of what we do at the receiver. And the only real technical difference here is we had to normalize the transmit beamformer. But otherwise, it's all the same probability of error derivation. I didn't go through it again. And the same intuition that we're coherently combining. So any questions on this, these calculations or this derivation here? Yes? Yes. Right, yes. Okay, so we'll get to that here in a second here. Let's see. All right. Yeah, so that's exactly the next thing I wanted to mention is that so this requires this knowledge at the transmitter here. And, you know, we know from doing all the labs. Now, in the lab is a little bit cheating because your transmitter and receiver are on the same, you know, computer. So there you also have it at the transmitter because you have it at the receiver here. But in reality, you know, your transmitter is sitting over here, your receiver is over here, and transmitter doesn't know the channel. And there's different ways to get that information. The most common approach is what's called feedback. And so I can have I can use the fact that each of these is actually a transceiver, and this is two-way communication. So, you know, the transmitter and receivers are taking turns. And so I can use what's called a limited feedback channel to convey information about the channel estimated here back to the transmitter. And why it's called limited feedback is that you have only a little bit of rate allocated for sending this feedback. You know, you can't send you can't estimate your channel and then quantize it into 1,000 bits and send those 1,000 bits back. That would be too much here. And so the limited feedback idea is you quantize this h here. This is, sorry, quantizer function, not Q function here. I'll make it like that. And so you quantize that h, and then send the quantized version back to the transmitter. And then in the transmitter, generates a reconstructed h based on the quantized values here. And so this is a whole theory actually associated with this, and this is something my group has done a lot of work on. But it is also, it's in a variation of this is in 802.11n, it's in LTE, it's in WiMAX, so it is a rather common approach here. What was interesting that we did from a research perspective was really realizing that because of the optimum solution here has this structure here. And there were two observations. One is that this vector here, so if you look at this right here, there's NT complex numbers we have to quantize. But because we've made it unit norm, there's one dimension that we can subtract off. So now it's 2NT minus 1 numbers we have to quantize. And then the second thing we realize is that this here, where I've taken alpha equals 1 over norm of h here, actually the performance doesn't matter whatever alpha you pick. So that's actually a second thing that you don't have to quantize. So you can always factor out an arbitrary phase. And so then, you actually, instead of quantizing 2nt real numbers, you can actually get away with quantizing 2nt minus 1 real numbers. And there's a way to look at this as being a manifold valued signal and exploiting structure. So, this is like topics of several PhD dissertations. I will talk about this more extensively in the space-time wireless class here. But anyway, it's a good question. Any other questions? Yes?
The different channel estimation of H1 to HND related to each other if we go in space and the location if we know and we relate different.
You're talking like with multiple transmit antennas, multiple receive antennas? Which one? I mean, the channels, you have to estimate the channels.
So are the channels related? So suppose I have single transmitter and different receivers.
Yeah.
And the channel doesn't change much, then maybe because of the different phase centers, we may calculate the shift in the edge phase and maybe we can.
Oh, I see what you're saying. Yeah. So this comes back to the assumption that we're usually operating in when we're talking about exploiting diversity is that the antennas are separated far apart so that there's really no phase coherence across the array. So it's not like a phased array that you'd find in radar or something here. The idea is that the antenna is spaced such that, let's see, it's really like this here. There's one antenna here, one antenna here. So there's multipaths coming in from all different directions. And the idea is that they're spaced far enough apart so that each multipath comes in with a slightly different delay. And so when they all add up, they end up with a different phase and different amplitude. Whereas the usual assumption, kind of a phased array, is that the antennas are so close that it's like a single wavefront coming in, and it's only delayed by the slight difference as a function of the angle there. And so we don't have that assumption here. For performance analysis, we assume they're independent, but in reality, they are correlated, and there can be, as an extreme, the example that you're giving, and the other extreme is this example where they're independent. And so the practical system will operate somewhere in the middle. But what that means is that you cannot assume too much about the channel, right? Because just because it can happen that there's a scenario where it's deployed such that it's phase coherent, you can't exploit that because it's not always the case. So now you could build an algorithm that was smart and took those correlations into account.
So that means for mining system, we calculate H for each channel.
Yes, yes. Yeah, we will do that. Maybe it's either next Monday or Wednesday we'll look at the channel estimation. Yeah, and it's even a little bit more tricky because not only are we going to calculate it differently for each channel, we also have this whole issue of the fact there's multiple transmit antennas. And so just like this naive approach doesn't work for diversity, we also can't send the same training on all the antennas and estimate the channels. We have to actually do something smarter at the transmitter too. Receiver, we can estimate it easily. The transmit side is hard. All right, any other questions here? All right, now what's the time here? Oh man, time. All right. Okay, so that was transmit diversity here. Now, let's take a short break here, like really short break. And I found an article here, this is again off of RCR Wireless here, and I expect you to read the whole thing here, but this is interesting that, so the FCC is looking at allocating more frequency spectrum for use for wireless, either for like Wi-Fi. This actually is not clear here. This is Wi-Fi or cellular, but they're looking at releasing 100 megahertz of frequency around the 3.5 gigahertz. And this is sort of interesting because there are incumbents already like in that band, and they want to allow those incumbents to stay there. So the incumbent is the person that has like the license to the spectrum already. And so it turns out there's the incumbents are authorized federal and grandfathered fixed satellite services users here. And so the 3.5 gigahertz band now is used for radar, as well as non-federal fixed satellite services, for receive-only space-to-earth operations and feeder links here. And so what they want to do is, so the idea is that this band is being used in a couple outdoor settings. And so they're thinking about, well, maybe we can make the band allowable for use indoors, and if people don't use a lot of power, it won't interfere with these outdoor users. And that setup is generally called a cognitive radio. So what's going to happen is that the users operating on a secondary basis will have to give preferential treatment to the incumbent user, and will have to communicate in such a way that they cause minimal damage to that interfere. And that's called, the current users would receive protection from harmful interference from all other users in the 3.5 gigahertz band here. And so this will lead to essentially 100 megahertz of spectrum, deployment of small cells, and what's called spectrum sharing here. And all this for 100 megahertz of spectrum, so not a lot of spectrum. I mean, it's I guess more than we have in the 2.4 gigahertz ISM band. Would essentially double that. But a lot of extra work for that here. Any comments, questions?
This is also unlicensed band?
It looks, it's not clear yet, but it looks like, yeah, I read this a couple times, and it wasn't obvious if they were talking licensed or unlicensed to me. So it may actually be unlicensed here. But they're talking about small cells, but I think they're also considering Wi-Fi a small cell. So that's why I had gotten confused. Yeah. Other comments?
They are using outdoor also, indoor also, no interference. So are there, what steps they are taking so that interference shouldn't be there? I mean, is the coding going to be different in both of them, or what is that thing which will keep? Because for outdoor some penetration is required, but for indoor penetration is not required, and the same frequency is used. So how they are trying to
Yeah.
not interfere?
Yeah, I mean, the signals are going to propagate, and in theory, there's some residual signal everywhere here. So it's really, there's a couple different ways to approach the problem, and this has been a big topic of research in cognitive radio. There's one aspect of spectrum sensing. So if no one is using the spectrum right now, then there's no one listening, right? So then you're not really causing interference because no one cares at that point. Now, if someone is using the spectrum, then the question might be, can you do something such that your received signal falls in their noise threshold, under their noise threshold? So, if you're far away and I transmit at a low power, by the time my signal gets to you, it'll be so low that it's below your receiver noise. Of course, now the problem here is I don't actually know where you are. So then you have to design a system to be very conservative so that I can assume that you can be reasonably close, so I always transmit extremely low power. Yeah, I mean, without feedback from the other users, you're kind of limited in the suite of techniques that you can use. But that's kind of the idea. So there's like spectrum sensing, see if someone's available there, and if there is someone there, trying to do something that causes minimal harm. And if this was more general, then you could cause a little bit of harm, and but if there was feedback, you could do a lot more smarter techniques. So. Anyways, I think it's exciting here to get more spectrum, because that means more opportunities for wireless engineering, more radios, more antennas, more basebands. All right, now let's talk about another application of multiple antennas. This is the Alamo T Code. And so what this is, all right. This is a different way of using the transmit antennas that does not require knowing the channel. And so that's why it's really cool, among other things. Let's see here. So 7. Okay. All right, so Alamo T Code. So this is an example of what's called a space-time code. And a space-time code is essentially, is not necessarily an error control code. It is generally used to mean a way of mapping symbols to the antennas for diversity gain. Now, by getting diversity gain, we're also going to presumably improve the error rate. But it's not necessarily there for the purpose of correcting errors. Now, you can combine these with other error correcting strategies and come up with a more complicated space-time code. Now, the Alamouti code is a very special example for only works for 2 transmit antennas. And but it turns out it's extremely elegant. And it's actually part of wideband CDMA. This is like essentially the first release of 3GPP. So this is something that's implemented in most commercial cellular systems at this point. So let's go through like the key idea here of this Alamouti code. And what I'm going to do is I'm going to just give you the idea, then we're going to go through and kind of show why it works. The way this came about is also really interesting because this came about in probably 1997 when transient diversity was just starting to be explored. And so this was a really cute trick that someone named Alamouti came up with, and it turns out to be, to have been very practical here. Now, of course, the Bell Labs, Lucent patented it, and so then, companies don't want to put this in wireless systems because they have to, perhaps license those patents. So, but anyways, it in itself is really elegant. Now, we represent the Alamouti transmission technique using this matrix here. So what we're going to do is we're going to take 2 symbols. It's called the symbol S1 and S2. And this is going to be the symbols I send across these 2 transmit antennas during the first time period. So this is first time here, instant. The second time period, what I'm not going to do is send S1 and S2 again, because they're just going to combine the same way. So you can think of different permutations. Well, what if I send S2 and S1? There's reasons that's not a good idea. So what Alamouti came up with was this tricky approach where in the second time slot he sends minus S2 conjugate, S1 conjugate. Here. Now, it's going to turn out that both the negative sign and the conjugate actually have significance. And notice that this conjugate operation here, it's not linear in the complex space. So you can't get the conjugate of a number by applying some linear transform to it. You'd have to, it's linear if you look at complex as being like a 2D, a point in a 2D plane. Okay, so what we're going to do now is we're going to write an input-output relationship that corresponds to this code here. So we're going to write in the first symbol here, so we're going to write y1. This is what we receive in the first time instant. It's going to be square root of ex over 2, h1 s1 plus h2 s2 plus noise. And in the second time instant, second symbol period, we receive square root of ex over 2, h1, and this is going to now be minus s2 conjugate plus H2 S1 conjugate plus noise. Now, one of the first steps we want to take is we want to get rid of the conjugate because we are after the symbols. So we're going to take the conjugate of y2. We get EX over 2 minus H1 conjugate S2 plus H2 conjugate S1 plus V2 conjugate here. And now what I'm going to do is I'm going to take this y and this y, I'm going to stack them up into a vector matrix equation here. So I'm going to put y1 and y2 conjugate here. And I'm going to write this as square root of EX over 2. Now what I'm after are these symbols here, S1 and S2. So I'm going to put S1 and S2 here. And then I'm going to put the noise over here. So then the question is what goes in this box here? Well, so we just have to follow through here. So this is going to be this row times this column. So we look over here, this is H1 times S1 plus H2 times S2. So we put that here, H1, H2. Now let's go here, the second row. We have H2 star times S1. So we're going to put H2 star here. And we're going to put minus H1 star here. And then we can call this here, we can write this in matrix form as y equals square root of EX over 2 H S plus V. This is going to be like an equation that we'll see when we talk about MIMO communication. So now what we're going to do is we're going to go through and multiply through by H conjugate here. So we're going to actually multiply through by square root of EX over 2 H conjugate. Actually, I'm just going to multiply through by the H conjugate here. Okay. So let's look at H star times Y, which is going to be equal to square root of EX over 2 H star H S plus H star V. Now then, the question now was what is H star H here? So let's go through and, just like this was in kind of in undergraduate days, let's go through and actually do this multiplication. So first of all, let's write out H star here. So H star is conjugate transpose. So that's going to be H1 conjugate, H2 conjugate, H2 minus H1 times H1, H2, H2 star minus H1 star here. So this is H conjugate, this is H here. Okay, so we're multiplying both of these together here. Now, so let's go through here and look at this here. So we multiply through H1 star H1 plus H2 H2 star. So that's going to be equal to H1 magnitude squared plus H2 magnitude squared. Now let's look over here. Now we get H1 star H2 minus H1 star H2. Cool. So that goes to 0 there. I'll do the same thing over here. H2 star H1 minus H1 H2 star. Oh, again goes to 0. Now we go over here, we see we get H2 star H2 minus H1 H1 star minus. So that's again H1 magnitude squared plus H2 magnitude squared. So this is equal to H1 squared plus H2 squared times 0, 0, H1 squared plus H2 squared here. All right, so now, what does that mean here? What that means is that if we plug this back in, to that original equation, that h star y is equal to square root of Ex over 2 times h1 magnitude squared plus h2 magnitude squared, 0, 0, h1 magnitude squared plus h2 magnitude squared times s1, s2 plus v1 and v2 here. By multiplying through by this h star, see, look at this right here. We have this times s1 plus 0 s2, 0 times s1 plus this times s2. So this is actually equal to square root of Ex over 2, sorry, I forgot the h star here, times h1 modulus squared plus h2 modulus squared times s1, s2 plus this noise here. So what we've done is we've actually completely decoupled these two symbols here. So that's quite nice here. So that is like a major feature of this trick here. Is that by, so now keep in mind here, so we sent the symbols twice. We used a weird switching of conjugates and signs so that this effective channel matrix is basically is orthogonal. The columns are orthogonal, so we multiply it by its conjugate transpose, it gives us a scaled identity matrix here. And by having a scaled identity matrix, that means that the first entry of h star y is some scaled version of s1. The second entry is a scaled version of s2. They don't mix together. And that's like a amazing thing here. Now, we have one final thing to do, which is the performance analysis. Now, the problem here, from a performance analysis perspective, is that we have h star times v here. We have the channel times the noise. And so what we need to do is we need to look at what's the distribution of that noise there here. So let's look at the distribution of h star v given h here. So this is a, v is a Gaussian random vector, which we write as 0, comma, n naught times identity. So this is very similar to the Gaussian random vectors that you looked at on Monday, except that we have n naught instead of 1 there. And then now, we also know from linear combinations of Gaussians being Gaussian that h star v is also Gaussian, characterized by its mean and its variance. So let's look at the expectation of h star v. Well, that's equal to h star times the expected value of v, which is equal to 0. So that doesn't change. Now, for a multivariate distribution, to characterize the covariance, if it's 0 mean, we have to look at the expectation of a vector of the following form. So it's going to be here, in this case, it's going to be h star v times its conjugate transpose, v star h. And then that is equal to h star expectation of v star times h, which is equal to this. Remember, this is identity, n naught. This is going to be n naught times h star h here. But remember that h star h is equal to this right here. So this is actually equal to n naught times magnitude squared of h0 plus magnitude squared of h1 squared times an identity here. So what we can do here is to facilitate this. So basically what we're saying is that, I guess I need to write another piece of paper here. All right. So what we're saying is that the noise this noise vector here has uncorrelated entries. And further, those entries have variance n naught times h0 magnitude squared plus h1 magnitude squared. So we can treat this detection problem as being totally independent because those two noise values are uncorrelated. Generally, you can't do that. So now what we're going to do then, so then we can look at this here and we can say, okay, now let me just consider the detection problem where I have yk equal to square root of ex over 2, h0 squared plus h1 squared. What have I done here? h1. Sorry, I switched from 1 to 2. Sorry, let me go back here. 1 and 2. Here. Times s of k plus this vk of tilde here. What I can do to analyze the performance here now is look at the effective SNR here. So the SNR is going to be EX over 2 times H1 squared plus H2 squared, because this is real, magnitude squared. And then we have the variance of this VK tilde here, which we derived as N naught, H1 magnitude squared plus H2 magnitude squared here. So then we go through here, cancel this, and we get that this SNR is equal to square root of EX over 2, H1 magnitude squared plus H2 magnitude squared. So hopefully this looks familiar here, because if I didn't have the 2 here, sorry, there's an N naught here. Yeah. So if I didn't have the 2, this would look just like maximum ratio combining. But with the 2, I just have a factor of 2 penalty here. So this is like MRC looks like MRC, but we have an additional penalty here of 2. But that's actually is okay. We can just incorporate an extra factor of 2 in our analysis here. So then we end up with, you can just plug in here, probability of error is then going to be, less than or equal to n minus 1 over, ex over, instead of 4, we have 8 n naught, d min squared plus 1 to the factor of 2 here. And so the main differences with respect to MRC is just that this is, because of the factor of 2 difference here. So if we plot, and I didn't bring a nice plot of this here, but if we plot, this is SNR, dB, this is probability of error, and let's say we plot the, that's like the baseline case, that's like, let's see here, whoops. So this would be, let's call this here like the pure Rayleigh case, CISO. And this would be Alamouti, 2 antennas, and then this would be, let's say, MRT or MRC. But let's look at MRT because we have 2 transmit antennas. And that exact gap is going to be 3 dB gap because, 10 log 10 of 2 is approximately 3 dB. So with the Alamo T code, you get the full diversity you can get from those 2 transmit antennas, but the penalty you pay is this 3 dB of loss. And so the intuition for me is that what we're doing is we are spreading our information over the two transmit antennas. So we're sending the same symbols twice here. And because we have to do this trick because we don't know, exactly how they're going to add up in the channel. So we have to send each twice with a slightly different phase so that we can get both of them here. Now with maximum ratio transmission, we would send a symbol once, but we would co-phase it perfectly, and then send another symbol, co-phasing it perfectly here. So there's no need to sort of explore the beam space. We just can send one and we can send it again with the same beam pattern here. So effectively, this penalty for not knowing the channel is 3 dB. If you know the channel, you can do transmit beamforming. If you don't know the channel, you can do the Alamo T code. So these are different strategies here. Okay, let's see. All right, so let me summarize here. Alamouti. Some observations about the Alamo T code. Okay, so first of all, it achieves second order diversity. The Alamo T code loses 3 dBs relative to maximum ratio combining. Sorry, relative to maximum ratio transmission. It does not require transmit knowledge. So you don't need this feedback channel we talked about before. And then finally, the decoding complexity is low. Low because all we had to do was the conjugate, do that match filtering operation, and just do detection as we would normally. We'll see that when we look at other MIMO settings, detection tends to be more complicated. So this is like a very special case here. Now, unfortunately, this elegant Alamo T code only exists for 2 transmit antennas. There are different generalizations, but they lose something or the other here. So there are codes for 3 and 4 antennas, but you can't send as many symbols. So like maybe you can send 3 symbols on 4 antennas, or you send 4 symbols on 4 antennas in 5 time periods. So there's some rate loss. Or they require a little bit of feedback, or they require higher decoding complexity. So this is just a very special case that you just kind of get everything, but otherwise it's going to be more complicated. And none of those other codes have really, to my knowledge, been part of any commercial standards. So it's really just the Alamo T code that's received the most attention here. Now what's happened with the development of these different feedback strategies, this 3 dB, it looks like a small number, is actually significant in a real system. And so when you have feedback, you can easily get back 2 of those dBs. Getting the full 3 is hard, but you can get, because you're doing some quantization, so you can get back 2. And then feedback allows you to generalize to many more antennas and to different receiver structures, and so it's just generally a more flexible approach. But the Alamo T code is, it's definitely super elegant. But it's just been hard to generalize it beyond this. And there's fundamental mathematical reasons it's hard. It's not just that people didn't figure it out. It's that people prove that, there's only a kind of a limited set of scenarios, and those scenarios all have loss in one way or the other. All right, so that's the Alamo T code. Any questions on the Alamo T code? The derivation, the idea? Yeah.
X-axis. So where does actually that 3 dB
Well, the 3 dB is really going to be at the high SNR, but I mean, it's going to be, you know, it's going to be at the point of the SNR where these lines are straight here. Is that what your question is? Or it's not going to be, the 3 dB gap may not be over here. They're a constant gap, yes, because they have the same diversity order. So this is maximum ratio transmission, and this is the Alamo T code. So they both decreasing with exactly the same slope, because they both have second order diversity. But this one is, our upper bound is EX over 8 n naught d min squared plus 1. And with maximum ratio transmission, it would be EX over 4 n naught d min squared plus 1. So it's just a factor of 2. That's the only difference in the bound. And then the low SNR behavior is, you know, a little bit different. Other questions? Yes. Well, we're achieving it, it's spatial diversity because there's no variation over time. So we're using it, but effectively, you can look at this like, we're kind of like converting spatial into temporal diversity. Actually, it's not quite right here, but we're exploiting time to get the space. And if the channel varied between those two channel instants, this wouldn't work. And so people have tried to apply this like in an OFDM system where you do it on one subcarrier and another subcarrier, and because those channels are similar but not similar enough, you lose a lot of performance. We had some work on that years ago. So it's actually better to apply it to two separate OFDM symbols, the same subcarrier. There's different variations of that. Yeah. Other question? Yes. Well, the way we're defining diversity in the class is just essentially this, based on this exponent here. And if I have two transmit antennas, this exponent can be as big as 2. So, yeah, I mean, that's how we're defining it. There are more sophisticated ways of defining diversity based on outage probability. There's also ideas of diversity as applied to coded systems, which are different than uncoded diversity. And the results are different. Yeah, they're strange in some cases. Yes, other questions? All right, let's look at now, we have a few minutes left here. See, yeah, here we go. All right. This is one I forgot here. Introduction to MIMO communication. So the next few lectures, we're going to talk about MIMO communication, which is, you can view it as a generalization of transnet diversity, but it's actually something more than that. And so we're going to, in this lecture, I'm just going to talk about one of the key concepts, which is what's called spatial multiplexing. So 13, 14. So first of all, just the definition here. So MIMO stands for multiple input, multiple output. And essentially, we're going to look at system configurations where there's multiple transmit antennas and there's multiple receive antennas. And then between every transmit and receive antenna, there's a impulse response of a channel. And so in general, that may be something like HK comma M of tau, and the entire collection of channels is this multivariate impulse response. And so the way I index here is usually K equals 1 through NR, M equals 1 through NT. So this H of K comma M is the channel from transmit antenna M to receiver K. So there's a lot of things that you can do in MIMO. different strategy of the transmitter, different things of the receiver. There's multiple users. So we're going to focus on the special case of what's called spatial multiplexing. And in particular, the next few lectures, we're going to talk about flat fading, though we will generalize to OFDM. So we're going to consider flat fading. So now what I'm going to do is just explain the key idea of what spatial multiplexing is. So essentially, suppose that we have a stream of symbols here, S1, S2, etc. here. So spatial multiplexing essentially is it's actually a demultiplexing operation, but anyways. This is a serial to parallel converter from 1 to NT, just like we saw this in the OFDM case, right? We had a serial to parallel converter. That's effectively what spatial multiplexing is. So this is spatial multiplexer. And what that serial to parallel converter does is it takes these symbols and reorders them here. So we're going to get S1, S2 through S of NT, and then we get S of NT plus 1, S of NT plus 2, dot, 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 S of 2 NT, etc. here. And so this is the spatial multiplexing idea. And so it's important to see here that what we're going to do at the transmitter is we're going to take a bunch of symbols and send them at the same time. And then in the next time period, we're going to take a bunch of new symbols and send them. Now contrast this with the Alamouti scheme. With the Alamouti, we sent S1, S2, then we sent S2 and S1. Here we're sending S1, S2, then S3 and S4. So the idea of spatial multiplexing is going to be we're going to send more symbols because we can send multiple symbols at the same time. And why it works is that we're going to be able to detect them reliably as if we had, sent them in some sense independently here. So some background here. I mean, this concept itself. It's also called VBlast here. Which probably is not obvious why, because it doesn't have anything to do with really the system. It's called a vertical Bell Labs space-time architecture. Now see, here's an interesting observation here about naming of titles and papers and things. So the Alamo T Code, right, in his paper is called something like A Simple Technique for Transmit Diversity, something like that. He doesn't call it the Alamo T Code. That would be sort of arrogant to do that. But he didn't give it a good name. So everyone called it the Alamo T Code. Now, his colleagues who created this vertical Bell Labs space-time architecture, they incorporated Bell Labs in the name. So, of course, anyone who's not at Bell Labs doesn't want to use Bell Labs, so no one wants to use it. So they sort of marketed themselves out of the whole naming game here. So when I was at a startup that happened in 97, around the same time that this came out, we wanted to differentiate the name. And so I had proposed the spatial multiplexing idea. Again, even though really it should be spatial demultiplexing, but because it made sense, sort of like you're sending multiple things at the same time in space, because you're multiplexing in space instead of in time here. And so that was one of the main motivations, was to not have advertised Bell Labs, in our product, because that would be bad for a startup to be saying, hey, I'm using this Bell Labs modulation technique. Okay, do you have a license from Bell Labs? No. So anyways, that was sort of an interesting thing there. Now, another name that this goes by is also called spatial division multiplexing. And this happens in at least 802.11n and maybe 11ac as well. And they call this SDM here. Why do they call it spatial division multiplexing? Well, I asked them at one point when they were developing it, why they didn't use spatial multiplexing. And as I've mentioned before, a lot of times in standards, people want to come up with a different name to help distinguish their intellectual property from other previous intellectual property. So conceivably, one could have a patent that says, I claim a spatial division multiplexing system that has blah, blah, blah. And then someone else could argue, and then they could argue, well, it's not spatial multiplexing, it's spatial division multiplexing. And then they would, hire a bunch of high-paid expert professors to argue whether spatial division multiplexing was the same as spatial multiplexing, and they'd eat up a lot of lawyers to get paid, and it's a whole enterprise on its own there. But yeah, apparently it gives them some advantage to rename things, and so it infuriates me that they do this, but they just seem to do it in all the standards. They give everything a new name. Multi-cell MIMO they call comp or something else. Anyways, sad fact of our field here. Now, spatial multiplexing concept, as part of 802.11n, 802.11ac, 3GPP, starting from release 7 and up, and it's part of, LTE advanced. It's one of the distinguishing features of 4G, et cetera, here. So normally when people are talking about MIMO, they're really talking about spatial multiplexing. Like if a marketing person is talking about MIMO. That's not the only thing you can do with it, but that's the one that gives the higher data rates and tends to be the sexier one to sell if you're a marketing person. Oh, we got spatial multiplexing and MIMO, and we get, gigabit per second, and so it's a marketing term there nowadays. So I guess we've run out of time here. So I'll explain the mathematical model for MIMO next week, and then we will talk about maximum likelihood detection, zero forcing receiver, and then the following Wednesday we'll talk about channel estimation, synchronization, then get into MIMO FDM. So that's it. 14.